Hello everyone, this is Pallavi Pujar from Rasayanika. So today we are going to discuss regarding the 18 electron rule, which is very important for the CSIR NET exam. So in case of many things, that too when it comes to specially organometallic compounds, the metal stability is mainly considered, right? So overall, the 18 electron rule, how exactly you are going to apply and how you are going to calculate the metal-metal bond, and as it is simplified version of EAN rule. So EAN rule will be very difficult in order to solve the organometallic concept, right? So just we have to go through the 18 electron rule. So now you can see that the statement what exactly you can follow for the 18 electron rule. So according to this statement, whenever you have the thermodynamically stable compound, okay, so the thermodynamically stable transition metal will be possible only when it has 18 electrons in its valence shell, right? So any metal that is transition metal in organometallic compound, it must have 18 electron in its valence shell. Then overall what we can say, it will be attaining thermodynamically stable. Okay, the stability mainly focused with respect to the 18 electron rule, and overall what I can say, so overall you can say that the 18 electrons in the valence shell is mainly focused. So coming to this statement, we focus that overall the metal d electron. So in case of transition metals, we know that there are d orbital, right? So the d orbital where it will be having the valence shell electrons, so it must be equal to 18. So in order to approach the 18 electron rule for every organometallic compound, you have to follow certain steps. Okay, so just let us look at the steps what you can follow. So the steps you can follow here. So firstly, it is you have to calculate the total valence electrons of the central metal atom. Suppose you have given some kind of X and Y type of complex. Okay, so X will be your central metal atom and Y will be the surrounding ligands. And the ligands where you have the Y, and first you have to calculate the total valence electron of the central metal atom, and then go for the identifying the number of electrons will be contributed by the each ligand, that is Y. So Y is each ligand, how many electrons it is contributing towards the metal complex, and then overall you have to check for any charge is present overall on the complex. Okay, so now you have the X and Y 4 type of complex. If it has certain minus Y type of charge, like minus Y will be what? The charge will be minus 1, 2, 3 and all. Okay, so if it has the charge, then you have to calculate that accordingly, either it is positive or negative. And then overall you have to calculate the total valence electron count of the each and every compound, and it must be equal to 18. So you are applying 18 electron rule. In order to check the stability of the molecule, you have to concentrate on the 18 count. Okay, so this is what with respect to the steps what you can follow when you are approaching the 18 electron rule. Now coming to the key table whatever I have shown here. So specifically when it comes to 18 electron rule application, so you can go for two methods. So one will be your neutral atom method, another one will be ionic method. So you can go for two ways also, but most often all of them they prefer the neutral atom counting method, where it will be easy for you also. So when you go for the ionic method, it will be bit difficult. In order to overcome the difficulties, you can go for the neutral atom counting method. So you can see the table here. So overall the electron contribution for each and every ligand with respect to their terminal and bridging position also is being mentioned. So with respect to any organometallic compound, you can see, so sometimes you will be having the dinuclear clusters also. In case of metal nitrosyls, metal carbonyls, you are going to get Fe3CO12, FeCO9 like that, right? So in such type of compounds, you have to consider the ligands, whether it may be at the terminal position or else it may be in the bridging position also. Alright, so because of that reason what I can say, you can go for this overall table along with respect to their contribution to the organometallic compound. So you can see that the neutral terminal anionic and bridging neutral and bridging anionic, bridging alkyne, then NO, it may be linear also, bent also. How long it will be able to donate the electrons, means how many electrons it will contribute towards the organometallic compound, that is important. And now coming to the next part is just let us solve one problem. So one of the interesting problem is Fe3CO12. So in case of Fe3CO12, as you can see the picture, like the structure of the Fe3CO12, you can see two type of Fe and CO overall in the structure. So this is what one type I have shown as A, and this is what overall B part, that is two types of Fe and CO environment you can see. And overall what you can say here, the first one A, as already I have mentioned, that is Fe with 4 terminal CO and 2 Fe bond. So this is what one Fe you have, along with that the 4 CO terminal groups are presenting towards the Fe, and apart from that 2 Fe metal bond you have, right? So 2 Fe metal bond you have, and what I can say, this is part A. Now coming to the part B type of structure unit, you can see, so where it will be, just let me choose different ink, it will be this one. So where it will be having 2 Fe centers, okay, so 2 Fe centers you have, and where it will be having 3 terminal carbonyl groups. Apart from that, on this also, so both are presenting same, so identical to each other, and then one CO here, one CO here. So these are two what the bridging CO group, that is bridging carbonyl groups, and this is what I have mentioned it as Fe with 3 terminal CO and 2 bridging CO and 2 Fe bond. Alright, so now let's calculate the total valence electron count of this compound must be equal to 18. So you have to approach for the 18 electron rule. So now coming to the first part, that is part A, where you have the Fe. So Fe electronic configuration, or else the valence electron will be how many? It will be, just let me show, that is D6S2. So D6S2 matlab 8 electrons, right? So there will be 8 electrons. Then coming to the next, where you have your carbonyl, right? So CO in the sense what? It will be having 3, that is 4 terminal you have. So you are considering the part A unit, right? Part A unit of the structure. So A, you have the carbonyl group. So 4 are there and it is terminal. Always we know that the terminal carbonyl group will be contributing always 2 electron each. So 2 electron each, then again it will be equal to what? 8, right? And then what else you have? You have 2 Fe bond, that is metal bond you have. So just let me mention it as Fe bond. Okay, so how many? 2 you have and 1, and then it will be equal to 2, right? So overall now you can calculate, so 8 plus 8 plus 2, so it will be equal to 18, right? So the part A of the structural unit, it has attained 18, and now coming to overall this part, okay, that is part B. So coming to the part B, just let me erase this. Okay, so coming to the part B, where you can have the Fe, okay, the same iron you have, and its configuration is D6S2, right? And you have here again 8 electrons. Apart from that, again CO you have. So just let me mention, it is 2 type. You have one terminal side, terminal type, another one will be bridge type. So now if you have terminal type, so how many you have? You have 3 terminal CO. So 3 terminal CO in the sense 3 into 2. So always it will be contributing 2 electron, right? So it will be equal to 6. Now coming to another type of CO, which is bridging type. So bridging type, when it comes, so again it will be what? So how many you have? You have 2 bridging CO. So 2 bridging CO, 2 into 1 you have to consider. So whenever you have the terminal CO, then it will contribute 2 electrons. If it is bridging carbonyl group, then it will donate you 1 electron. Okay, so now it will be equal to 2. Apart from that, you have 2 Fe bond. So just let me mention that. Okay, so Fe bond will be 2, then it will be into 1 equal to 2. So if you calculate overall 8 plus 6 plus 2 plus 2, it will be equal to again 18. So overall structure is attaining 18 electron rule, right? So overall the electron count is equal to 18 electron. Then what I can say, this molecule or this compound is thermodynamically stable organic compound. Okay, so this is what with respect to 18 electron rule. So like this way you have to approach for each and every transition metal organometallic compound, and so that it will be easy for you also. And when you go for the EAN rule, it will be a bit difficult. In order to overcome that difficulties, the 18 electron rule is mainly simplified in its own way. Okay, now remaining part we'll discuss in the next session, and thank you, and this video will be definitely helpful for you.